Hi everyone. So what we're going to do in this video is we're going to prove a quirk of special relativity that hinges on the fact that the speed of light travels the same speed regardless of the motion of the source or the motion of the observer. And what we're going to prove today is something called time dilation. And that's the fact that under the assumption that the speed of light travels the same for everyone, moving objects or at least events happening inside moving objects, appear to run more slowly than they normally would if they were stationary. So to set up this quirk, or to at least set up the proof of the quirk, we're going to introduce this object called a light clock. So a light clock is composed of two mirrors, and what happens is a pulse of light is emitted from one of the mirrors, it bounces straight up and gets reflected and bounces straight back down. Okay, and this is a pulse of light. So we're going to call this distance here L. Okay, it's just the distance between the mirrors. And we're going to say that one tick of this clock occurs when the light travels from the bottom mirror, which we'll call A, up to the top and then reflects back down to A. Okay, so we're going to label this time T0 or T0. Now, because light travels at a speed of c, we can actually describe this time period using the variables in the problem. So because time is equivalent to distance over speed, and because this light pulse has to travel a distance of 2L with a speed of c, that is the time interval of one tick of this light clock. Okay? Now, this is supposing that the light clock is stationary within our frame of reference. Okay, so the light clock is moving with us, or it's not moving at all, where we're not moving at all. It's in our own frame of reference. Okay, so according to our point of view, the light just bounces straight up and then straight back down. Okay? Now, imagine you then watch a spaceship fly past, and they have their own light clock. So what will you observe in this case? Well, I'll have to draw 3 stages here, and each stage corresponds to a little bit of time later when the ship has moved past us a little bit more. Okay, so we'll say that the ship is moving past us with some velocity v to the right. Now what we will see, looking at the light clock in this ship, is the pulse will be emitted from the bottom mirror, just like in our normal light clock. And because the ship is moving, it will appear that this light pulse is also moving to the right as well. Okay, so if I'm going to draw the path that we observe this light pulse taking, as the ship moves to the right, this light pulse will travel that way. Okay? It will hit mirror B, and then it will be reflected back down to mirror A. Okay? What you've got to remember is this light clock is moving past us. So these 3 diagrams represent different stages as the ship is moving past. Now, because we know the speed of the ship, we are going to label the time that it takes for the light pulse to travel from here to here as TAB. That is the time it takes, from our point of view, watching this light clock move past, the time that it takes for the pulse of light to travel from mirror A to mirror B. Now, because we've labeled that time interval and we know how fast the ship is going, we can describe the distance the ship has moved in that time period. So this distance here, okay, if you just remember speed equals distance over time, then the distance that the light clock has traveled, which is the same as the distance that the ship has traveled, is equal to v times the time interval, which we could just call TAB. Okay? And that is since distance equals speed times time. All right. Now, the length or the distance between the mirrors of the light clock has not changed, so this distance here is still L. Okay. Now, because we know the distance between the two mirrors, L, and we know the distance the clock has traveled in this time interval, which is v times TAB, we should be able to work out the distance the actual light pulse has traveled. Okay, this diagonal line here. Okay, now we can just use Pythagoras' theorem, and we find that the distance the light has traveled in that time interval is equal to the square root of L squared, so that's that short side squared, plus this short side squared of the right angle triangle, which is, now it's going to be V times TAB all squared like that. Okay. Now, the total distance that this light pulse travels before it gets back to mirror A, well, that's just twice of this D that we just wrote down here, okay? So the total distance, that's equal to 2 times D, and we know that D is equal to the square root of L squared plus, I'm going to write this a bit differently. I'm going to sort of expand those brackets. So instead of V TAB squared, I'm just going to write V squared TAB squared. Cool. Now, because I know the, before I move on to that, we've described that the time that it takes for the light to travel from here to here, that's TAB. So we want the total time the light takes to travel from A to B back to A over here. Now that's just twice of TAB. So the total time of this trip we'll just call T. That's equal to 2 times TAB. And then what we can say from that is, well, TAB is equal to half of the total time, half of T. Okay? Now, you might see that according to someone stationary with respect to the light clock, you might notice that the distance the light has to travel is shorter than the distance that someone observing the light clock move past, shorter than the distance that light has to travel, because that light travels in a sort of diagonal direction, okay? And because light travels the same speed for any observer, you should realize that the time that it takes for the light to travel in a moving light clock will be longer than the time that it takes for light to travel in a stationary light clock, simply because the light has to travel a greater distance. Now, our goal here is to try and work out a relationship between the time taken for a stationary light clock to tick once and the time taken for a moving light clock to tick once. And the rest of this point onwards is just using algebra, okay? So what I want to do next is I want to write the total time taken for the moving light clock to tick. I want to write this in terms of its speed and also the distance that this light has to travel. Now, we just said that the distance for a moving light clock pulse to travel is this part here. So the time taken to travel the entire distance can be written as distance 2 times L squared plus V squared. Now, instead of TAB, I'm going to replace it with half times T, because I know that's the relationship between TAB and the total time. So instead of TAB, I'm going to write it as half T squared. And the light travels at a speed of c, so the total time taken for one light pulse of a moving light clock to tick once is given by that relationship there. So let me do some algebra now and start pulling apart what I've written here. So I'm going to expand what I've got in there, and I can write this as 2 times the square root of L squared plus, now half squared is 1/4, so I can write all of this stuff here as V squared T squared over 4. And all of that is still over C. Next, I'm going to multiply both sides by C to get rid of this pesky fraction. So multiply both sides by C, I end up getting the following. CT equals the square root of L squared plus V squared T squared over 4. Next, I'm going to square both sides to get rid of the square root. In doing so, I will get c squared t squared on the left, and on the right, I'll simply just have L squared plus V squared T squared over 4. What I'm going to do now is basically, whoops, I've gotten rid of a 2 somewhere. Let me go back. I've mucked up my algebra. The 2's still here. Okay. And when I square both sides, that 2 there turns into a 4. Sorry about that. Now, basically when I expand the right-hand side, the 4 is going to multiply with the 2L, the L squared, and I will get c squared t squared equals 4L squared plus V squared t squared. Okay, that's better. What I'm going to do now is I'm going to subtract V squared t squared, put it onto the left-hand side. So I'll end up getting c squared t squared minus V squared t squared equals 4L squared. I can then factor out the t squared from the left-hand side, end up getting t squared times c squared minus v squared. That's still equal to 4L squared. What I can do now is I can divide both sides by c squared minus v squared to just get t squared. That will equal 4L squared over c squared minus v squared. I'm going to square root both sides, so I can isolate t, solve for t. We're going to ignore the negative part of this square root. Just focus on the positive part because we don't care about negative time. So the square root of the right-hand side will give me square root of 4L squared over c squared minus v squared. I can simplify the right-hand side a little bit, noticing that in the numerator I've got 4L squared, and the square root of that will be 2L. However, the denominator is still the square root of c squared minus v squared. Now I'm going to do something really weird, and you'll see why in a second. I'm going to factor out a c squared from the terms underneath my square root. So we'll get this t equals 2L over the square root of, I'm going to factor out c squared from both of these. So I'll get c squared times 1 minus v squared over c squared. And what I wanted to do that for is I wanted to get a c squared factor under my square root so that I can square root the c squared and end up with just c. Again, you'll see why I'm doing that in a second. So 2L over square root of c squared is just c, but I still have this 1 minus v squared on c squared factor that's in the square root. And one more thing I'm going to do is I'm going to combine the v squared over c squared into one thing, all squared. So I can write this as t equals 2L over c times the square root of 1 minus v over c squared. Okay, so we've reached this point here. What I want you to look at is this part of the fraction, the 2L over c. Okay, and if we go back up to the top, you'll notice that 2L over c was the original time taken to tick once of a stationary clock. Okay, so I can replace the 2L over c at the bottom with t naught. So I'll get t equals t naught times, and I've basically got 1 over the square root of 1 minus v over c squared. Okay? And what we usually do is we then lump all of this stuff together here, and we give it a name, and it's actually called the Lorentz factor. We're going to just use the variable gamma. Okay, so it's a Greek letter gamma. It's sort of like a weird Y shape, right? Where gamma is equal to 1 over the square root of 1 minus v on c squared. Okay. Now what you might notice is any value for v that you put into this equation, it will spit out a value for gamma that is 1 or greater. Okay, so this gamma factor, this Lorentz factor, it's always greater than or equal to 1. So what that tells us is that the time taken for a moving clock to tick is some factor times a stationary clock's tick. Okay, so moving clocks run more slowly, and because we've just set this thing up as a clock that somehow measures time, this can be applied to any time interval between two events. So the time interval between any two events of a moving frame of reference is greater than the time between the same kind of events in a stationary frame of reference. Okay, and this is known as time dilation. Okay, the fact that when something's moving, the things that are going on inside that moving frame of reference appear to be running more slowly. Okay, so time dilation. So if you had a friend who had an identical watch as you, and you saw that friend moving past you in a quickly moving spaceship, you will notice that your friend's watch seems to be ticking more slowly. Okay, and because the watch is ticking more slowly, and because a watch measures time intervals, then everything that's going on in your moving friend's frame of reference will also appear to be moving slowly. So you'd probably see them walking in slow motion, you'd see them aging more slowly than normal, and this is just a quirk of special relativity. It's just a quirk of recognizing the fact that the speed of light is the same for everyone, regardless of the motion of the source or the motion of the observer. Okay, and that's it. Okay, so we've basically derived this equation here, time dilation equation. And again, just reiterating, events in a moving frame of reference appear to happen more slowly than events in a stationary frame of reference. So that's it. All right, we've derived time dilation equation. There you go. All right, we'll use this in examples in class. See you later.